You have to use the arrows to move between.
Okay. So thank you very much. Today I shall talk about our story work with Johannes and Lawrence Schwarzhofer on grammar inequality on singular statistical model. So grammar inequality is classical reason in statistics about optimal estimation. Okay, so my talk is divided in three parts. The first part I recall the theoretical framework of our work, that integration parameterized measure model. That is the work I have done by us before. The second part I shall talk about our work on the general grammar inequality, and in the last part I show that our general grammar inequality is optimal, and then in 5 minutes certainly left that for question, and possibly I also comment something more if there are no question. So let me recall the framework of our K-integration parameterized measure model already developed in our book Information Geometry by Johannes Schwarzhofer, myself, and Nihat Yao. So that I already yesterday comments after the talk by Mark after talk yesterday about what is new in our framework in comparison with previous theory. So that let me recall some notation. First, I denoted by P omega the space of the probability measure on some measurable space omega. So I draw the sigma algebra here, and mu omega space of the finite measure of omega. S omega, that is most interesting space, the space of unsigned finite measure, and then S omega mu naught, that is on the space dominated by some measure mu naught in omega. So the definition that I denoted M omega p is that parameterized measure model which parameterized by some Banach manifold. That means that possibly infinite dimensional. P is parameterization, that means a map from M to the space of the finite measure on omega, and this space sit inside the space of the finite measure omega. Each is a Banach space is a total variation norm, and that is actually that's our new idea here, because that's a very natural idea in mathematics. Put something do not have the nice structure inside something is a nice structure, and the nice something has a nice structure here is a Banach manifold of the sign finite measure is the total variation norm. And once you have the target and domain Banach manifold, you can define the notion of the differentiable map. And because it's an infinite dimension setting, there is a different notion of the differentiable map, and you have to here use a Fresher-Sion map. Certainly you can have the weaker notion as the action comments later. So that M omega p is called the statistical model if the image is inside the space of the on probability measure in omega. So now the second step, that is also our new idea and a new lesson in such this direction, that we define the notion of the logarithmic derivative and of the map, the parameterization map, as CC is some parameter here. So we define by the red ink here. That's a logarithmic derivative is defined by the right hand side. That means that's just how to say Nikodym-Radon derivative. And why you can have not Nikodym-Radon derivative because it has some lemma. That's yes, you can define it because it's dominated by the P omega. So that is another lemma. It ensures the correct definition of the definition here. And this lemma is also quite simple, but nevertheless that nobody discovered before us. So that means that using this lemma, you can say that the derivative is when defined is only in space of and 1 omega p omega. And then how this a new definition and related to the classical definition. That means that classical definition it considers the family of the dominated measure. Then you define it in terms of the density function, and then to see that density function arises, function is two variable. Is x is in element in omega and psi is a parameter. So usually it define in terms of partial derivative, and then when you have this equality because that motivate our notation BV of log here. And yes, the answer is yes, as that model has some kind of regularity and the positive density function. Otherwise, I mean that yesterday I told that we don't need any existence of dominated measure. Therefore, we don't discuss about the density function is positive or not. You can still define the notion of tangent. And the next thing that is also new here, that it defines the notion of k-root of measure. That is not completely new because some people already discussed it, but they never discussed in the completely in as we do. So the first innovative our measure space is the order, partially order space. It has the notion of the order within measure when it depends on the dominated or not or equivalent or not. Yeah? And therefore, once you have this notion of the order, and you can define the notion of the in this case of the direct limit. Yeah? And then we define the space of the k-root of measure of the direct limit of the space of the Banach space of the L on here. And this usually direct limit is have very terrible structure. But here it proves that it's a not terrible thing. It's a Banach space. Yeah. And then Banach space is a norm. And how to once you have this norm, you can define the map P 1 over K go to from M to space of the sign measure and the eraser of the order to S 1 over K here. Yeah. Because using this is limit. So it a little bit complicated, but not so. Everything is. Then now it gives a new definition that a parameterized measure model is a K-integrable is a map by P 1 over K is a Fraser-Sion map because the packet space and domain space are nice Banach uniform. And then you have the theorem that a parameterized measure model is a K-integrable if and only if the function of the K norm of the tangent value defined on the tangent space is continuous. So the second definition is a kind of weak continuity And then the previous definition is called strong continuity Sion map. And the theorem says that the two notions of continuity are the same, equivalent. And then I have to say that you have the several paper on the integrability, and then this theorem unifies that all our definitions are equivalent, so you can use any definition on the first or second paper on this book. There are no problem, and we also discuss in our books that how is this theorem is related to other notion in classical statistics. And another Fisher metric defines a very simple way that you take the any parameterized measure model that takes and too long because you remember that the degree of log is the element in the L1, but if you have the is a k-integrable, so that element in L2, and you can take the pairing of it. And now then you consider the space of the how to say parameterized measure model. It may be not has some curve length of the parameterization because that is also not so terrible for us. And then if you have the curve length, then it takes the Gaussian down of the curve length, and then it considers the Gaussian space, extension tangent space. And because the Fisher metric has the curve length also on the curve length of this of P, and then it descends to the Gaussian space. And the Fisher metric on the extension tangent space is non-degenerated. And then we, because it has the Fisher matrix here, and then it can define the fiber-wise completion of the reduction of the extension tangent space with respect to this metric, and it goes, yeah, in this noted in this way. And now I can almost now close to state our general grammar inequality, but because working on very general settings, so that is infinite dimensional, so we need to pose some condition of regularity. It's easy to be checked such as a fulfilled for finite dimensional case or continuous case, but nevertheless you want to introduce very general conditions. That's the first condition, that is it defines some space, and the KP is on the function is lying in the and the KP for any.
Just hold it for this meeting.
I see.
Just don't speak up.
Okay, I see. Then it's say something is regular if the norm of the function f over and the kp is locally bounded. Yeah, so locally bounded is such a now it defines the space of the feature functions. That's a feature function that are taking value in some topological vector space, possibly infinite dimensional, and that is feature function. That's every coordinate is a regular belong to that space. So an estimator is called regular if every coordinate of it is regular in that sense. And now I define the Z quadratic form that replaces, that is nothing else, that's a differential of the phi L sigma is quadratic form. And the theorem says that if the estimator is a phi regular, then the difference of the variance and the new function, the quadratic form, is a positive semi-definite quadratic form of the Luan space of V. So that is a little bit, how to say, very exact thing. So I just say that if I see everything is a classical noise, Phi is a coordinate mapping, B is final dimensional, then because the classical grammar inequality for bias estimator that is writing in this way, and that if you don't have any bias, then it's a even more classical inequality that's the inverse of the Fisher metric here. Okay, then now I say that our grammar inequality is optimal. That means that when it's optimal, then when you have the variance of estimator equal that inverse of the size of Fisher metric if you done on complicated notion. And then statistical model admit efficient estimator, then the grammar inequality is called optimal. And here I have two examples. First is quite a trivial example. That means that I take the classical case of the regular minimal full exponential family and mean value parameterization. And everything is okay. We have no such unbiased Phi efficient estimator, and how to make it go to the singular just blow up of the manifold along any arbitrary submanifold, and that is then you have the strictly singular statistical manifold which admit by the Phi efficient estimator, but that is quite a cheap example. So the second example is more or less non-trivial. That is Foucault-Mizu infinite dimensional exponential family, and then Foucault-Mizu introduced new family of the infinite dimensional exponential statistical model using reproducing kernel pair space theory. Here that's how he considers it. And then I say that using very big conditions. That means that I can produce infinitely many examples of such a thing. And that's I claim that then zero exists. Certainly I have to find a Phi map such as space of the Foucault Mizu infinite dimension space under that very big condition admit Phi efficient estimator. Okay, then so here reference first that is in our first paper where we define the notion of the integrability using the fixed continuity of the Fisher metric. And then the book where you almost have many things from here, but the first paper where introduce the notion of the arms is a logarithm, derivative, and the idea of using the balance space of finite measure. Okay, and here's a paper by Foucault-Mizu when he introduced his infinite dimensional exponential space. And then in our archive paper, we discuss our relation. Our relation is other people lesson in the grammar inequality, not only classic but quite recent, and there are a lot of the paper on it, hundreds of the paper on grammar inequality, and that book is on static ways they consider most full version of grammar inequality in context of classical mathematical static, and here's a book of Watanabe on singular statistical model. He says that they are everywhere in statistical learning theory. Thank you very much.
Thank you for your talk. Do you have any questions? I have a question, which is what was the original motivation for this generalization?
Generalization, that is you see that's a generalization, but is, the most important that in the notion of boundary estimator, because that's the idea. Estimator is have many terms in statistical learning theory that it calls as a predictor, estimator, and everything that's very important. But you don't want to estimate the full information of the probability measure. You want to estimate only a certain feature of it. Therefore, it introduces the notion of the variety. And then infinite dimensional thing is, I think that's quite an important thing, but the people do not yet completely understand how to do it. So that is two things that why you need to do in infinite dimensional. The second thing why you do is only certain variety estimation, but not completely full, because I believe that we can never know in infinite dimensional setting full information about the probability measures, and we define only partial information, and that I believe is a philosophy. Yeah. And of course, its question is how you consider parameterization. Parameterization has a better description of the statistical model. Certain, I just want to say that many theorem here you can also extend is a difficulty for the case of the unparameterized statistical model, but with a bigger notion of differentiability.
Thank you for the talk. I think it's around the 90s, in the setup of Banach-Lee groups, I think the Harp in his book, or I'm not sure if that's the right reference, but he referenced this manifold of densities as an example of a Banach-Lee group that pretty much fulfills all the conditions that you need. How is this different from your setup?
So if you consider only density, then it's everything density is only set of the dominated parameterized measure model of dominated measure. And one of the advantage of our approach, we don't need such a parameterized measure model consists of the dominated measure. So our standard is more general. Almost enough that people consider only density, because they cannot do in the general case. I mean that if the density you multiply with the sum of base measure, then you have the measure. But not conversely, because to get the density function, you have the need to some dominated thing measure, and you use the Nicodim-Radon theorem to get density function, right? So that's a density, you consider every classical static in terms of density function, that is only particular case of our case. And I have this some habilitation. I forgot the name, but if you are interested, they consider the infinite dimension space, module exponential space, where the measure, you cannot describe in terms of the density function.